Hello, everybody. Welcome back. Today we're going to be talking about Unit 3.10, which is all about solubility. So let's get started. So much of what we're going to go over today is actually going to be review of some topics that we have looked at before. So let's just kind of review what we've talked about before. And, solubility is all about, will something dissolve or not? And we said before that substances with similar intermolecular interactions tend to be miscible or soluble in one another. That word miscible is typically a word used when you're talking about a liquid solute being mixed in a liquid solvent. Like we would say, acetic acid is miscible in water. Soluble is typically a word we would use with a solid solute, okay? So the way that solute and solvent interact with one another is the true determining factor on whether something will dissolve or not. So let's review. Okay. Ionic solutes tend to dissolve in polar solvents. And we've got a little image there that is very similar to one that we have seen before. If you were to dissolve an ionic solute in water, let's say, the ions get pulled apart and what's called the ion dipole attraction is what occurs between solute and solvent. The polar solvent will surround each ion and be attracted to the oppositely charged ion. That's called ion dipole attraction. Okay, but again, it's the attraction between solute and solvent that is responsible for why salt dissolves in water. A polar solute will tend to dissolve in a polar solvent. Like ethanol, for example, will dissolve in water very, very well. Why? Because they will attract to one another. Ethanol and water both have the ability to hydrogen bond, and not just hydrogen bond to each other, but hydrogen bond to not just their own molecules, but to the other molecules. Ethanol can hydrogen bond to water. There's a force of attraction, again, between the solute and the solvent. Nonpolar solutes will tend to dissolve in nonpolar solvents. Again, as I keep saying again and again, because it's so important, there will be a force of attraction between the solute and the solvent. Now, between nonpolar things, the force of attraction will not be nearly as strong because the interaction will be involving London dispersion forces only, and those are relatively weak. But there is still a force of attraction. So let's look at a sample problem here. I'm going to read it to you, and if you want to stop the video and try to answer it on your own, great. Otherwise, I'm going to talk through it. So we've got a table of information here, and it says, use the information in the table below to respond to the statements and questions below. Your answers should be in terms of principles of molecular structure and intermolecular forces. The first statement says, identify a compound from the table that is nonpolar and justify your answer. Okay. So pause the video and see if you can figure that out. Not just which one is nonpolar, but how do you explain why? All right, hopefully you chose the molecule ethane, the one in the middle. Ethane is nonpolar, and your explanation should say something along this line. Because its shape cancels out the polarity of its bonds. Okay, in order to receive the point on a question like that, you would have to talk about shape and that there is no overall imbalance of charge, that all the charge is overall balanced. The easiest way to say that is the shape cancels out the polarity of its bonds. All right, here's the second part of the problem. It says ethanol is completely soluble in water, whereas ethanethiol has limited solubility in water. Account for the difference in solubilities between the two compounds in terms of intermolecular forces. So pause the video, see if you can answer that question. So hopefully you all notice that ethanol and ethanethiol have very similar structure. The only difference is that ethanol has an oxygen at the end and ethanethiol has a sulfur at the end. Both molecules are covalent. Both molecules are polar. So both molecules have the ability for dipole-dipole attraction with the water. But there's something unique about ethanol. Ethanol can form strong hydrogen bonds with the water, whereas ethanethiol does not have that capability. And then it says hydrogen bonding increases the attraction between ethanol and water, making it more soluble. So guys, when you're answering a free response question, you have to talk about the interaction between the solute and the solvent. Okay, you have to talk about the force of attraction between them and what kinds of forces there are. Okay, so let me review something with you, and then I want to show you something a little bit interesting. Okay, if you will recall a couple of lessons back, we talked about how oil and water don't mix. Okay. And the reason that doesn't happen, why oil and water are not miscible, is because the attraction between two water molecules and the attraction between two oil molecules, those like self to self kind of attractions are stronger than the attraction between water and oil. So they stick to each other more strongly than they are attracted to each other. Okay, they stick to themselves more than they stick to somebody else. So I always get the question, somebody's always wondering, well, wait a second. How do fish breathe? Okay, if you know anything about fish, fish breathe oxygen just like we do. However, they don't breathe it in the same way that we do. Fish are obviously underwater. Fish breathe dissolved oxygen, which, ladies and gentlemen, oxygen is O2. Now think about that for a second. O2 is a completely non-polar molecule. How in the world does oxygen dissolve in water? Oxygen is non-polar, water is polar. That shouldn't happen, but it does. Otherwise, fish couldn't breathe. So we said something non-polar like oil is not going to dissolve in water, but for some reason, oxygen can. Well, guys, oxygen, two oxygen atoms bonded to each other, it's a lot smaller than a gigantic oil molecule. And I don't know if you know that, but oil molecules are very large. Okay, so oil molecules, they're non-polar, but they have relatively strong London dispersion forces because they are such large molecules. They're so polarizable. Oxygen, O2, is a pretty small little molecule. And yes, it's non-polar, but what ends up happening, guys, is when a water molecule comes near it, and remember, the oxygen side of the water molecule carries a slight negative charge. Let me just write one little negative charge on there. Okay. What that does is induce a momentary dipole, and we've talked a little bit about that before, in the oxygen molecule next to it. That is going to cause the electrons to sort of scoot in this direction because that oxygen, let me circle it, this one is carrying a negative charge. That's going to repel the oxygens in this molecule away from it. And it's going to create a slight dipole in that O2 molecule. And it's just enough that they can have a very slight force of attraction. It's not strong. It's a very weak force of attraction, but it does exist. So is oxygen soluble in water? Kind of. It's what I would call sparingly soluble, but it's enough that fish can breathe. Okay. Another example would be carbon dioxide, ladies and gentlemen. Carbon dioxide is dissolved in water. That's how we have sodas. Okay. Carbon dioxide is also nonpolar, but because it's not a relatively large molecule, water is able to induce a momentary dipole that's enough that it can dissolve, at least sparingly so. So I just wanted to go over that with you because oftentimes I get students that ask questions like that. You know, you're saying that nonpolar things shouldn't dissolve in polar, and typically they don't, but they can. Okay. So I wanted to go over that with you. I hope you all have learned a little something today about solubility, and I look forward to seeing you next time.